Hey guys, how's it going? Welcome to another episode of Ferris Makes Demos. This is episode 45, which I called Compression Ramblings. And the reason is, I normally would do an emulator stream on Thursday, but I had a really long day. Just a lot of stuff I had to do at work and then in the evenings, or in the evening. And I'm in just kind of a weird, tired mood. And so all I'm thinking is that, I feel like I can't really get into anything other than what my mind is already thinking about. So I'm just going to hang out and talk about compression for a half an hour to an hour. And that's going to be my stream today. So I hope you guys like that. By the way, hi to guys in the chat. Dark Second, Unconditional Branch. Happy to hear you're tired also. 8 Little Bits, also happy to hear you're no longer alone. Alkama, Hugs, Daru2, Dark Second, Zakwar, Zao, SK Thess. Hey Jack Skater. Yeah, exactly, Daru2. I'm gonna decompress by talking about compression. So I've been talking a lot about the fact that I've been working on a 64K compressor for our intros. I think I've been actually working on actually quite a long blog post. I'm not going to show you guys the whole thing, but this is the mini map so far. It's long. And that's going to be talking in very, very fine detail about how our compressor works, and it even has a compression primer kind of section, and I'm just going all out with it, and I'm really excited to put that out, and I'm building the blog for it and everything. So at that point, that's when I kind of want to release all the details of our packer. Today, I'm not going to do that. I'm probably not going to talk that much about that packer at all, actually, because what I've been doing more recently, and this has just been more for my own fun. Essentially, here's what I think I'm going to do. I'm going to actually show you guys some actual numbers here. Only a little bit. I'm going to compress our intro Trash Panda with Crunchy, and then I'm going to compress it with our packer, and you guys can see the results. And then I'll talk about what I want to talk about. So I think this is the first, not the first numbers, because I posted this on Twitter too, these exact numbers, but it's kind of fun to see it. So Algecoma demos. Actually, no, I want to do this in Squishy Corpus. And actually, I need to make sure of something really quick, because things are kind of a mess with the different projects here right now. Or actually not. This is up to date with master. I think I'm okay. And if I do build.sh, this should work. Squishy's got a build. So Squishy is the name of the packer currently. I don't know if I'll keep that name, but it's just a working title. So if I run this, actually I run Crunchy first. So I've got this Squishy Corpus repo here that has just a bunch of executables that I test with. Most of them are executables that we in Logicoma have made, but there's a bunch of other ones. There's a conspiracy intro in there. There's a couple control alt test demos in there. A few Poo Brain ones. There's one from Approximate. And I think a few others. There's one from Pysic, and I think there's one from Macau Exports too. Procyon, good call, but in that case, I don't think I can do that because it needs to count up, because I actually use ECX for something in that code, and that can't go backwards. Maybe I can make that work, but that's we'll get to that later. But that's very much the kind of optimizing that's going to go on in that particular file. Anyway, in this case, I just want to do Crunchy. I mean, there's several versions of this. This is the one I test with, is this 023A4 ASM07 version. And there's really no reason to use a lot of these parameters. I like to use the ref size one, though. just do out.exe here, and then we'll compress. Actually, we'll do demo scene, logicoma, trash panda, party, uncompressed exe. So if you run this with Crunchy, this gets down to a compressed size of 59707 bytes, and then the total executable 63488 bytes. So this is pretty good. This is like 62 kilobytes altogether, and this is really the number we care about. Actually, this delta is really what we care about, but this final executable size is the actual thing we care about. This matters a bit, but then there's this plus the overhead of the uncompressor, or decompressor. So in my case, in Squishy's case, we'll do this, and then I think we do Squishy corpus, demo scene, logicoma, trash panda, and then we'll output to out.exe. And this takes a little bit longer, so this also took like 1.18 seconds in Crunchy, and with my packer currently, this will be a bit longer. Takes a few seconds. There it goes. 7.7, that's a lot slower actually than it normally runs. It normally runs about 5.5 seconds. But anyway, this gets down to the final size of 61440. So this beats Crunchy by a full 2 kilobytes on this intro. And most of that comes from the actual compressed size here. You can see it's literally a couple thousand bytes. In fact, 3,000 bytes smaller. And then our decompressor on just like roughly is about 700 bytes larger than Crunchy's. And that mostly has to do with the fact that the x86 modeling is a bit more complicated in Squishy. And also the other models are a little bit more complicated. But not that much. Like the actual, the sort of bitwise predictions that it makes, the way it does that and the way it actually models different contexts is not that fundamentally different. It just takes sort of some newer ideas from the pack series that didn't exist when Crunchy was made. And the models are a little bit bigger, a little bit more expensive, but they just predict a little bit better. But then kind of the major difference between Squishy and Crunchy is the way it does x86 modeling. And the way I do it is, I'll get to more of this in the blog post, but essentially I have a scheme that can find both vertical and horizontal correlations in code, whereas Crunchy will separate the bytes into different streams in order to force either vertical or horizontal correlations that it ends up modeling. So mine ends up being a little bit more general, and it compresses a little bit better, but it's a bit slower and uses a lot more memory. In fact, I think this even says the BSS size, so it's like 260 megs or something in memory, which is fine. Whereas Crunchy uses like 30. So it's a lot of cycles and a lot of memory, but it does compress a couple percent better. And if you graph this stuff, you can basically draw on a log plot of like compression ratio versus time. It's essentially linear on that logarithmic scale, where there's Crunchy, pack 8, and then our compressors right in the middle, which is basically where it should be, I feel like. And of course, we're going to have to tune some of this. Like I'll probably use less models for our music disk, which is going to be a much larger uncompressed size, and that determines how fast this actually is, all that stuff. So lots of details, but that's basically where we're at with this one particular intro. And just to prove to you that it actually runs, so we can do out exe and then in about 5 to 7 seconds, because it takes that long when I'm streaming apparently. There the intro comes up and it works. So yeah, so that does pretty good. I'm pretty happy with these results, but one of the big things here is that this decompressor is a bit bigger than I'd like. So just for fun, what I've actually been doing is something that I call squishception. And what that actually is a compressor for this decompressor. So there's several ways I can get this down. Like I said, it's about, I'm estimating here because I haven't really like checked how big the actual decompression code is in Crunchy, because I would need to hack it to kind of output that data. And I haven't done that, but assuming it's about 1.5 kilobytes, which is what Rig has claimed on his blog, that seems about right looking at the code. So assuming that, then we're 700, 800 bytes larger. And I would expect with the kind of modeling that we're doing that we should be around 500 bytes larger. So WizardTube says, did I test it with other demos? Yes, I have a whole corpus full of lots of demos. But this is the only numbers that I want to show right now. But generally, we beat Crunchy anywhere from 1 to 3 kilobytes, except for a couple intros. And I think the worst we do is we're half a kilobyte larger. So it's not too bad. Anyway, mainly what I've been doing is trying to get this down, and that's a mix of like hand optimizing the assembler code that this is implemented with, and that's gotten to a point where we're getting kind of diminishing returns, and I've had to kind of look at the architecture a bit more and really change how a couple of things are implemented to really get some of these gains. So need to look into that a bit more, but at the same time, it's getting so boring to do that I've considered, okay, what if I actually just write another compressor? So we have like a stage 1 decompressor that would decompress this decompressor and then jumped into it. And then this would actually decompress the actual intro. There's actually a third stage, which is now the second stage, where it has to like fix imports and do some other things. But essentially just add that stage in front of it that actually compresses this. And the funny thing is I've actually gotten surprisingly good results with that, and that's kind of what I've been thinking about and wanting to talk about today. There's several approaches to this. What I've done initially here, this is squishception. I'll just run it right now, and it gets this 2398, which you'll notice is a little bigger than that. Yeah, because it includes the data too, and it's actually a little smaller because both stages can actually use the same entropy coder. So we're just sticking that in the stage 1 stub, and then the stage 2 stub, which is this, can then remove it. So it actually has a little bit less data than these two put together. And then I can get it down to 1842 bytes so far, which is pretty good, except that this has like a 230 byte decompressor for that other stage. And then that's still pretty good, but I've actually gotten a little bit better results if I use the Microsoft compression API or the Windows compression API, where I get it down to 1903, so it's like 50 bytes bigger, but then assuming that all this really needs is the function imports and a couple function calls, that should be around 80 bytes, because that stuff has to be uncompressed, and we have to follow like the actual Windows imports for that. So assuming that's about 80 bytes, then this ends up winning by like 80 bytes or something. So I'm still actually working on improving this and playing with a lot of ideas, because having a custom coder here is more fun. And if it's at all possible to still beat that number with a small enough depacker, then I want to do that. So I've just been exploring that for fun. And it looks like with this approach, we're already going to save like 300 bytes. And then with the other approach, with the Windows compression API, we'll save like 350 bytes. So it's kind of cool. So we would use the Windows compression API to decompress our decompressor, and then our decompressor to actually decompress the intro. Because the decompressor that we have in here is a big context mixing decompressor, or it's an arithmetic coder with a big context mixing model. And that model compresses way, way better than anything the Windows compression API will give us. So we still want to do it in multiple stages like that, not just rely on the Windows compression API to do everything. But yeah, so it looks like we'll be able to get this down to something like this. So I think that's pretty cool. Procyon says, how much work would it take to port to ELF? I don't think it would be too much work, actually. The compression, of course, is platform agnostic, and it's all just like handwritten assembler. The biggest problems would be like linking, because to build an executable compressor, you have to parse the executable itself, and then you also have to build a bunch of your own like stub files, and you have to implement like enough linker functionality to link all that together. And right now that's all just been because we already have to parse executable files. I just build all the other. In fact, if I cat build.sh, no, that's in Squishy. Cat build.sh. I actually build everything as COFF object files, just because it's the same format once you get past like the PE header. So I think that would have to be, at least the parsers for all that stuff would have to be redone, but this could all be made to work with ELF. Imports in particular would probably be one of the only actual platform specific things here, other than like the format of the headers, which isn't that big of a deal. And that that actually is not that bad either. So the symbols are resolved after unpacking. So we resolved 2 symbols before unpacking, and that's load library and get proc address, so that we can actually load all the other ones after we're done unpacking. And we don't do anything like import by hash for compatibility reasons. Like we could probably save a couple hundred bytes doing that, maybe. I actually don't suspect we would save that much because there's a lot of function names, and I'd rather avoid collisions and potentially like have this not break with future versions of Windows. Like generally because this is targeting 64K, you kind of want to care more about compatibility and that kind of thing, just because like you can afford to spend a couple hundred bytes just making sure that your intro is going to still work in 5 years. Whereas 4K, you wouldn't care as much about that. So we don't do that much like header folding or anything or overlapping. Like I think the only really overlap we do is we take the PE header and we put it over the MZ header. And then we just drop a bunch of the other like data directories and stuff. So really we only have the imports to import those 2 functions. Again, we could get those through like some PEB walking and stuff that the import by hash guys do, but I just don't think the savings are worth the potential compatibility problems later. I think that's a decent balance. What I've mainly focused on is, of course, the compression itself. So I think that's kind of the right way to spend that effort. I might, however, still want to play with that though. Like, I mean, there might be a case where we just need that extra 200 bytes, and maybe that'll get us there. But I don't really suspect that that's gonna be what happens. The other thing is too, like, with Crunchy, like speed is a big factor here too. So even the compression could be a lot better, but you have to balance that with how much time you actually spend to decompress. Brand says, how fast is decompress? It's symmetric to this compression speed, so it's going to be around, for this intro, it's usually about 5 seconds. And that's somewhere in this sort of pain threshold. So where I got that number is like, I think on Rig's blog I read that when he compressed debris with Crunchy in 2007, it took about 8 seconds to decompress. So that's just like, okay, about 8 seconds is like the unbearable threshold. So if I'm well within that, then I think this is okay. So about 5 seconds is not the most comfortable thing, but given the fact that it's still lower than what his tool did 10 years ago, I think it's reasonable. Nice, Alkama. Of course I use NASM. Yeah, I mean, if you do normal dynamic linking with Windows too, like you're also gonna waste a lot of space. So that's why the only 2 symbols we actually import are from kernel 32, and that's load library and get proc address. And then the rest we still do by hand. It's just we don't do it with like import by hash. We do it where we store just smaller versions of those string tables for all the function names or ordinals, because we support that too. We just load whatever imports the original executable was doing, and we just store them in a lot smaller tables. So we still handle the imports ourselves. It's just we don't use import by hash. Which I think is a good balance of not wasting all that stupid header space, and also still being really compatible. But that's more of a matter of taste. Again, you're talking about like the order of a couple hundred bytes maybe that you really save there, because like those hashes probably don't compress really well, and those have to be uncompressed anyway. Maybe the strings compress better. I'm not actually sure. I would have to actually try both approaches before I would decide which one's actually better. And of course, the code to do imports when you have the addresses for those 2 functions is not that bad, and you spend like 60 bytes to get those addresses via the normal mechanism that's built into Windows. So it's really not too much. Like this is the whole import code, so it's just not a lot. Nice one, Zao. Hey, Daniel Cullen. Yeah, the decoder you're seeing here is actually the decoder for this second stage that I'm playing with, or the first stage, I guess, where I'm compressing the decompressor, and this is the whole decoder. not the smallest thing in the world, but it's also not the biggest. A couple hundred bytes for this is pretty good, especially this arithmetic decoder is really nice. I actually, this is kind of fun. I explored first actually trying an ANS coder. So RABS, I think, is the variant, which is range-based and binary, which is essentially a drop-in replacement for this in the decoder. But I actually couldn't get it smaller than this. This is about 20 instructions for the arithmetic coder, and for the ANS coder, I could get it to about 24. And the reason is because you only ever express when you're working with a bitwise model like this, you only ever express one of the two probabilities for symbols. You either the probability is going to be 1 or it's going to be 0. And when you do the ANS update for the 0 case, let's say you're predicting the probability the symbol's going to be 1. When you do the ANS state update for the 0 case, you then have to flip that probability and then do all the same math with it to do the state update. And like one of them has a bias and the other one doesn't. So like you end up with these two branches that either are almost the same but kind of not, or you try to merge those code paths, but then you need a lot of registers to hold all the intermediates. And the fact is we need a lot of the other registers ideally to be preserved in the code that actually uses this. And so it just ended up being a real pain in the ass. So this ended up being like 5 or 10 bytes smaller or something by the time I actually got everything working. Maybe it was more than that. I don't know. It's pretty rough, but just looking at the code side by side, this was a lot more convenient to just do an arithmetic coder. And in terms of like accuracy, the difference is basically negligible, or like precision, and then speed doesn't matter at all because it's totally dwarfed by the model. So I went with an arithmetic coder. Jump versus jump short doesn't actually matter in NASM. The assembler's going to figure that out. Pyro says, I know nothing about compression, but can you increase compression speed by dividing data into blocks and compressing them with different CPU cores? Not really, because when we're doing compression that achieves the kind of ratios that we need to achieve here, we're totally speed bound by the model that actually makes predictions. So let me paint a bit here. You can basically think of it as sort of two things. Like this is a context mixing compressor. So what we do is we look at the whole intro as just like a stream of bits. And for every bit, what we're going to do at every position, we're going to predict what the next symbol is going to be on a spectrum. So we have like a number from 0 to 1. It's actually not 0 to 1 because we do this integer arithmetic, so it's 0 to 4095. It's a half open interval, and that doesn't really matter. But we predict like the probability that it's going to be a 0 or 1. So like let's say we predicted like 0.2 probability that it's going to be a 1, and then that's implied 0.8 that's going to be a 0. We feed this prediction into a coder, which is what's actually going to take. Like the encoder is going to take this bit and the prediction and gives it to the coder, and the coder then outputs the actual compressed bit stream. And then the decoder is going to, for every position, it takes the prediction just like the encoder did, and then figures out the symbol, and then might read stuff from the bit stream. So it's kind of this reversible process. But anyway, the point is that this step right here, where we actually make the prediction what the next bit's going to be, that is extremely expensive, both in terms of calculation that we're actually doing per bit, and also especially memory bandwidth, because we use a lot of memory and our memory access patterns are extremely random. So, or at least like they end up being random because we use a lot of hash tables essentially. And then with good hashes, you get a lot of random layouts. And there's something to be said too about like trying to optimize your hash function based on memory access patterns that you might actually have. But in the case of our compressor here, our hash table ends up with buckets that are already aligned on cache lines, and then we have 4 entries for those buckets. So it's 16 bytes per sort of predictor, and then we do hash tables where like a hash maps to one of these buckets, and then we might shuffle these around a bit. But then we're still kind of working within the same cache line. So like the next time we fetch one of these, or next time we look up another bucket, we're going to have to fetch another cache line anyway. So it doesn't really matter. There's not too much that we can do there other than having just a good hashing function and focusing on ratio there. I'm rambling a bit and kind of jumping back and forth, but that's just kind of how I figured this stream would be anyway. Procyon says, I'm aware of that, but shuffling around stuff increased the total size of the code because the offset got larger or not larger than what you said. Yeah, that's true. That's something we can play with too. Definitely. But yeah, it's kind of funny because like if you do an ANS coder, you actually have one less state variable that you need to maintain throughout the code. Than an arithmetic coder, because an arithmetic coder has to do, it needs two states, like a low and high bound on this interval that you're sort of reducing, whereas an ANS coder has one state, which is the part of the number you're looking at as you're compressing. So with like a range coder like this, which is actually what this is, range coder is just an arithmetic coder, but a nice small implementation of this. It's pretty much the value of the code variable is analogous to what you would have in the ANS state. But the important thing is that here we need two registers that we always have. So EBX is the code and then EDX is the range. That's like the bottom and top of the interval. And then the code we're compressing or code we're generating, and then the size of the interval. Whereas ANS would only need one, but again, when we do the update, just because of the way that the math works, you end up with like, you have to mask the state and then do a conditional on the mask, but you still want the original state in a register, because you're going to multiply the original state by a prediction, and your prediction might actually flip depending on if it's one of the bits. And then when you multiply that together, you still need the original prediction again. So that's like another register, like another temp that you need, because they need to bias it in the case that you do that flip. So it's like, I wasn't able to find some mathematical identities to kind of help shuffle that around. Maybe I didn't look hard enough, but anyway, it ended up being a few less instructions to just do the arithmetic coder and keep these two registers occupied always, but then never occupy any other registers for very long than it was to only have one register occupied all the time, but then have to use a bunch of temporary ones to actually do the update properly. And then again, for like the precision of the coder, neither one was particularly better. Like we're talking a couple bits difference, because they're both pretty accurate. Also, this particular range coder is not the most accurate we could do. We could, because this is built to output or input 8 bytes at a time, or input 8 bytes at a time in particular, or not 8 bytes, 8 bits, so whole bytes. So we lose a bit of precision there than we would if we wanted to use. So we're essentially using a 24-bit arithmetic coder here. We could use like a 32-bit one or 33-bit one even if we do some carry fun, but it's just easier to have this sort of byte-oriented I/O here, because otherwise we would have to have bit-oriented I/O on the other side of the coder, and we don't really save enough in ratio from the test that I did, where that really makes very much sense anyway. And especially since the reason I even looked at this versus ANS in this context was like, this is the decompressor, so this needs to be really small. And then I think if we're already paying for an arithmetic coder, paying for that and some additional bit I/O didn't seem very prudent. It just seemed a lot easier to, I don't know if prudent's the right word, I'm tired, but it just seemed easier to just do byte-oriented I/O beneath the arithmetic coder, and I don't think we'd gain enough to really change that. Anyway, so the sort of big decompressor that we have is this bitwise context mixing approach. And again, we're totally bound by memory access and compute in the model. So like trying to cut that down is not very fruitful. I don't need to save that. But this little decompressor, I went with kind of a different approach, and I just kind of wanted to talk about it because it was fun. So I decided that the first thing I would try is an LZ-based scheme. So you kind of have like two sort of major ways you can do compression, and most modern compressors, especially the ones that are biased for speed, do a kind of a mix of the two. But you essentially have these things that are based on entropy coding, and then kind of your whole compressor is based around how well you can predict what the next symbol is going to be. And you get all of your wins just from doing that prediction really well. And then on the other side, you have sort of dictionary-based compressors, which they will try to, instead of doing like pure entropy coding, what they will do is they'll replace parts of your message with smaller versions of that message. So for example, if you do like A, B, A, something like this, an entropy coder just working on this is going to try and replace each one of these symbols with like less bits. So assuming each one of these would be like 8 bits, if you look at these probabilities, you have like 4/5 probability that your symbol is going to be A, and then 1/5 that it's going to be B. And this doesn't look at any local statistics. It's just looking at how many, at our whole message here. And so we could actually figure out more or less how many bits this should take. There's something called Shannon entropy, which gives us exactly how much this should take, and that's negative log 2 of the probability. So in this case, if we do negative log 2 of 4/5, I'm just going to do this in the calculator here. So let's say our 4/5 probability is to be 0.8, and then we do our log 2. Does this have log 2 in it? I don't remember how to shuffle around logs. I'm just going to Google it. Negative log 2, 4/5. So Google tells me it's about, we'll do this here, or around 0.32 bits. And if we do 1/5, then this is going to be around 2.32 bits. Yeah, that's the identity Bamba. That's the one I can never remember. So, I mean, since we actually have 2 symbols, each one should actually be about 1 bit. If we wanted to like really be rigorous about this, then each one of these symbols originally is 1 bit per symbol. So this could be 0, 0, 1, 0, 0. So already if we replaced each one of these, so instead of this being 1, 1, 1, 1, 1 for bit counts, we could do 0.32, times 4 plus 2.32. And as long as that's less than 5, which is this sum here, then we get compression. And just do that math. 0.32 times 4 plus 2.32. And this is 3.6 bits. And our compression ratio for that is we can take that divided by 5, and then we actually want to do 1 minus that. So we can make negative plus 1. And that gives us about a 28%, in fact, exactly a 28% compression ratio. That's not too bad. So you can figure out exactly, like, given decent probabilities and the message, like how many bits this should actually take, and then this is your ratio, which is essentially how much you take off when you compress it. So this would be like a pure entropy coding approach, where we just replace all the symbols with some representation of the symbols that would take up as many bits as their probabilities imply. There's a lot of details when you would actually do this, because there's different ways to do entropy coding. Like you could do this with prefix codes, but in this case, you're going to get probably pretty bad compression with that because these probabilities are not very close to powers of 2. So you're going to lose a lot of precision there. And there's usually encoding details of like, if your encoder needs some overhead to transmit some additional state so that the decoder can decode it, like, it doesn't really matter, but you have sort of a spectrum of like ways to do this that are fast and ways to do this that are accurate. It's maybe not a spectrum. Maybe it's not that simple, but essentially you can just think of it like this. And then the other family of compressors we have, I'm actually going to open up another paint instance because I might want to come back to this. We'll go back for this same message. you have the dictionary ones, and what their whole idea is what you're going to do is replace these symbols with some kind of smaller representation, ideally. And so you would do things like, let's say our input alphabet is these characters. And so we can say like our input alphabet, A, is in the set of these symbols. And maybe our output alphabet, which we can call B. Maybe I can make this a little curlier, make this look more like a beta, just to differentiate these. This might be a set of, for example, a literal and a match. So we're just going to replace the alphabet with these different things, and we'll get a sequence that ends up being identical. But so like if we went along here, the encoder could say like, okay, A, we're going to replace that with literal A. And then we see another A, and I'm going to hand wave over how these might work, but let's just say we encode it as another literal A. And then we see B, we're going to encode that as literal B. And then we see A here, but what we actually see is that there's actually two A's, and we've actually seen that before. So what we can do is we can say a match from 3 positions ago and 2 characters long. So if a decoder saw this, we could say, okay, we see a literal A, so we're going to output an A. We're going to see another literal A, so we're going to output an A. We see literal B, so we're going to output a B. And then we see a match where we went 1, 2, 3 positions behind and copy those 2 characters. So we take these and we copy them over here as the match told us to do. So that's kind of what we're doing, is we're replacing these symbols with these symbols. And if you can imagine here that, let's say, we could imagine an encoding for this. So a literal might be marked with a 0 and a match might be marked with a 1. And then we might have, I don't know, these are pretty small numbers. So we could say like plus 3 bits, or actually 2 bits for the offset, plus another 2 bits for the length. And then a literal would actually also be plus 8 bits of the actual literal itself. So it's 1 bit plus that, but then you can see what I mean. So like literal A might be, or in this case, it would actually be plus 1 bit for the literal, because we decided that was going to be like 0 and 1. So if we encoded this literal A would be 0, 0. The next literal A is 0, 0. Literal B is 0, 1 plus that literal. And then the match for 3, 2 is going to be 1. And then the 2 bits for 2, or for 3, which is going to be 1, 1. And then the 2 bits for this, which is 1, 0. 4, 5, 6, 7, 8, 9, 10, 11. 11 over 5. We get a negative compression ratio here. This is a negative 120% because we've expanded the data in this case. But you can imagine that, like, let's say these were 8 bits each, then this would actually still already be useful. So I think it would be, because we'd have 1, 2, 3 bits plus 24 bits, so it'd be 25, 26, 27, 28, 29, 30 versus 8 times 5, which is 30 again. No, that's not right, is it? 8 times 5 is 40, so we actually would get compression there. And 25% would be our ratio. So, I mean, I'm just kind of like rambling here, but you can imagine this is more or less how it works. The nice thing about these kind of codecs is that they tend to be a bit faster. So normally we would say this is asymmetric. So if you're just doing this sort of context modeling approach, or this entropy coding approach, this would probably be symmetric with your encoder and your decoder, because your encoder is going to be just encoding symbol by symbol, and your decoder is going to do exactly the same thing on the other end, just symbol by symbol decoding. And then maybe your model, which is actually producing these predictions, is expensive, but you would probably have the same kind of model on the other side. So this like your compression time and your decompression time is basically the same. Here, it can often be symmetric. You often spend more time in the compressor, because like at every position, you're going to be like searching if there's anything in the history from what the compressor has seen or what the decompressor is assumed to have seen at that position. It's the same thing. So in this case, we want to search for this match, and then doing those searches and finding different ways to encode can often take a lot of time. Because the other thing here is that there's different ways we can encode this. For example, this second A right here, maybe having a literal was a bad idea, because a literal would have been 9 bits, whereas a match would have been 1, 2, 3, 4, 5 bits. So we can actually save 4 bits if we used a match that just had 1 byte backwards. So that match would have been, instead of this, or well, in this case we did 2-bit literals, so that actually would have been more expensive. But my point is, like, we could have encoded this as a match that's 1 byte back and 1 byte long, and both of those would have produced the same output sequence in the decoder. And so there's this whole thing about, like, what is the path through the input that we encode this as, and that we actually call that the parse. So, like, how do you interpret this input to produce this list of symbols? And that might have a lot of different concerns that sort of guide how you're going to do that. If you want maximum compression, for example, you're going to want to do a lot more searches, and you're going to want to try a lot of different ways to encode this. But if you want maximum speed, at least in your encoder, then you might want to just, like, sort of greedily take, like, the longest matches possible. And in some cases that is actually optimal compression wise, but in most cases it's not. Yeah, you can often chunk the data and use different, like, dictionaries. In this case, the dictionary is kind of implicit because it's just everything that the encoder and decoder have seen so far. But you can also supplement that with another dictionary that you can do searches in, and you can maybe replace that for different blocks at the cost of maybe having to supply that dictionary per block. But maybe that still works out that you get such good compression from that. That's fine. Lots of ways to do this. And then there's what most modern, so we call this LZ family of coders. Dictionary encoders is more general, but, like, this particular, like, replacement by these literals and matches tends to be this LZ family. And that comes from LZ 77 and 78, which is these old algorithms that Limpel and Ziv made, just 2 last names of some guys. And these algorithms generally work pretty well. But the interesting thing here is that when you're actually doing these encodings, like, I just talked about encoding these as just individual bits. But you could have several different ways that you could do these encodings. You could have them be byte-oriented or nibble-oriented, which is what a lot of, I think, like, LZ4 does. Some of those modern codecs that are more tuned for speed. Oh, Lempel, not Limpel. So I actually didn't know that for years. That's funny. Anyway, so what a lot of these will actually do is, when you have these output of these literals, these matches, then you can actually do entropy coding on those. And that actually tends to work out really well in terms of, like, a speed ratio trade-off. If you do some really cheap modeling on, like, how likely different literals are, and the different parts of these matches might have sort of different contexts in which they predict different symbols and different kinds of modeling, that turns out to work out really well. And I think most modern codecs that are optimized for decoder speed especially are doing that to some degree. Because you can get really cheap models, or you can do, like, have sort of semi-stationary models where the models are only updated once per block. And then you might have, like, a simple update scheme, but, like, for that block, you're going to use the same models, same statistics for all these different symbols here. And then you can, like, interleave coders and stuff. So you can do, like, the entropy coding or decoding really, really fast, given that your symbols are static. And even take advantage of, like, SIMD. In particular, the ANS coders have some really nice properties with how they output to the bit stream, and the fact that the encoder and the decoder are in exactly the same state when one of them writes and the other one reads. Arithmetic coders don't really have this property because they have to, like, there's some corner cases with when you reduce this interval thing that mean you have to, like, look at other bits, so the encoder might not write out some of the bits for a long time after they've been seen, whereas the decoder is always reading them in more consistently. But ANS doesn't have this problem. Like, whenever the encoder is write bytes, or whenever the encoder is going to write bytes, the decoder is definitely going to read those bytes right away. And so it makes it a lot easier to, like, interleave different streams that contain bytes output by ANS coders. And then you can do things like pull or, like, decode a couple streams in parallel using SIMD, and then do renormalization that just might read bits for some of the streams. So it's actually pretty cool. Again, that's pretty much only possible if you're very seldomly updating the symbol statistics, because otherwise you're going to lose all of that, like superscalar benefits to, or superscalar or SIMD benefits to just the fact that you have to update your model, and that's often expensive. For the binary case, it's not that expensive, but then you're doing it a lot more often. But for like multiple symbols, like if you're doing something that's nibble oriented, then that update can actually be pretty expensive, because a lot of these entropy coders also have like different preconditions, like all of the symbol probabilities need to add up to 1, and so when you want to adjust the probabilities, you have to like essentially do a divide per symbol to sort of renormalize all of that. And there's ways around that, and there's ways you can do that, but they tend to be kind of expensive. Anyway, so in particular, this decompressor that I've been working on, squishception. This is an LZ codec. So what I first started doing when kind of implementing this is I wanted to try a byte-oriented LZ. And the reason why I wanted it to be byte-oriented is because I wanted to make the decoder as simple as possible. So it might do something like a literal would be a 0 byte, and then another byte, which would be the actual, so 0, and then the actual character here. And then a match might be the length, and then you can see like, okay, a match of length 0 is actually a literal, but this might be the length for a match. And then another byte for the offset. And then this might be an encoding. It turns out this does pretty badly. I think I could only get it to expand the data. So already I wanted to do like bitwise IO. So then I compressed this so that I still took this thing where like, I think I separated the whole thing into packets just to try something. And there's tons of ways you can do this. This is just the way that I tried. Where instead of doing both literals and matches, I actually would always do a packet had a match length, and then a match, either a match offset match length, match offset, and then literal always, and a single literal. So if the match length was 0, you might not do a match offset, but then the decoder is always going to read a match length. If the match length is not 0, it's going to read a match offset and do that copy, and then it's always going to read a literal at the end. And that's the scheme I more or less went with. So with that, and then making each of these take a different number of bits, like I could do a match length in like 4 bits, and then a match offset in 11 bits, and then the literals, of course, are 8 bits. Then like the smallest packet you have is like 3 plus 8 bits, so 11 bits for that. And then the longest you would have, which would include the offset, would be 22 bits. And doing this with a decent parse actually started to compress the data, not enough to make up for the decoder, because the decoder at that point, as soon as you're doing bitwise IO, it already starts to kind of get a bit large. I mean, we're talking about the order of like 100 bytes or so, but still. It didn't compress well enough to just get away with that. So then I just was like, okay, well, if I'm doing bitwise IO anyway, I might as well make the bitwise IO do some entropy coding. So that's why I came out with this encoder. And that's fine, except as soon as you're doing entropy coding, then you need a model. You can actually describe a model really tiny. So like, if we still constrain our match lengths to like, what am I ended up with? What did I end up with here? It's all up here. It's actually all up here too. It's easier to read here. Yeah, match length is still 3 bits. Match offset is still 11 bits. Literal bits is 11. Those kind of symbols. So the idea here is that this is still going to be described as 3 bits, and it's still going to be described as 11 bits, and this is always going to be 8 bits. But then these different bits are going to be encoded with different contexts. And so like the main idea here is that as we see a lot of these different matches, as we see a lot of these different packets, like especially as we see like a lot of the literals are actually going to contain the same byte. And so we want to sort of make, as we go through our file, we want to sort of adapt how we predict the bits of the literals to match what we've seen in the file before. So we're going to do what's called adaptive modeling there. So every time we see a literal, we're going to see the 8 different bits of the literal. And for all those different bits, we're going to select a different kind of context that this is in. So the main idea here is just that like if we see an A, we could have either an A or a B. So the first time we predict what that bit's going to be, or what the symbol's going to be, we don't really know what it's going to be. So we're going to predict even for both symbols, which is nice because then we don't get any compression or expansion. We're going to get 1 bit from that. But then after we've seen like an A, we can adjust this prediction. So it's like out here now. So we're pretty sure it's going to be an A. And then if we see a lot of A's, then this will continue doing that. If we see a lot of B's, it will go the other way. But the point is that over time, we can kind of learn. So this kind of model is actually really simple to construct. In fact, I can just show you the code for that. Let's see. Yeah, there's just this array of initial predictions, which normally start at 1/2. I actually don't start them at 1/2 because this data tends to be biased towards 0, so I start at something else. But then, yeah, this is just the straight prediction. I think we just use the prediction directly. But then the update rule just takes the symbol from 0 to 1 and let's see. Yeah, I think I need to explain something else here first. So when we're gonna predict a symbol, we're gonna use what's called context. And in this case, I kind of roughly describe the context as, okay, we're gonna encode a literal, but it's a little more than that. So the main idea here is that if we're going to encode a symbol, again, we have our alphabet, which, let's say some symbol is in the set of, whoops. We have symbols in an alphabet. And alphabet is some set of like A or B or whatever. In this case, we can just say it's 0 and 1, because that's what it's going to be. The main idea with context is that, like, let's say if we looked at this, man, I'm really losing myself here. Let me sit and think a minute. Quality streams. Okay, I can actually just explain this really intuitively, just like this. Let's go back to this case. And let's just assume that we're going to encode symbols like this, A's or B's. Or actually, let's make these bits now. I think we're there already. And let's just say we're going to really simplify this idea of context. So for every bit position, we're going to predict what the next bit's going to be. And let's just say that the context is in the context of what we've seen before. So at this point, the context is nothing because we haven't seen anything before this. And in that context, we really should just predict half and half. Our prediction that's going to be a 1 should be 1/2. And that turns out to be pretty good. It might actually not be. Like, if our file tends to have more zeros than ones, then we actually shouldn't predict that. And that's actually, this compressor actually takes advantage of that, which is kind of funny, but we'll get to that. But then let's say this next one, we actually do have a bit of context here because we've seen a 0 before. We haven't seen any 1s before. We might still see a 1. We're not entirely sure, but we can maybe predict. Let's say we did like 9/10 that it's going to be a 0. And for this particular data, that's pretty good. At the next position, though, we've seen 2 zeros and we haven't seen any 1s. Then we might even say like 99 out of 100 that we're pretty sure that this is going to be a 0. And in that case, we're really wrong. So this is going to take up a lot of bits. In fact, I want to calculate that. Negative log 2 of 0.99. Or actually, it's the other way. It's 0.01. So it's 6.64 bits.
Wait, what did you say?
1 second. Oh, sorry. No, anyway, so that's like not great. And then these ones, okay, we're not as sure that it's going to be 0 anymore because we just saw 1. So maybe we'll go back to 9/10. And then it was pretty good again. So the next one we might suggest like 99 out of 100 again. Anyway, the point is that like we can implement a model like this pretty simply. And the way we would do that is we would just start at a number, usually 0.5. And so we use that to make a prediction, and that's where we just use the prediction directly. So we kind of use it, and then we have an update after every symbol. So we use it to make the prediction, then once we've seen what the symbol actually was, then we try to update this to better predict what the next one's going to be. So a really easy way to do this is to take the actual symbol, so you can do plus whatever the symbol was, and I guess the generalized version of this update rule is it's going to be, so we call this P. So we can do P prime. So the next one is going to be P plus the symbol minus P times, I don't know, some learning rate, which we can call L. And usually L is a couple percent. But of course you can tweak that with different learning rates. So if you want to do this in fixed width math or fixed precision math, you can do something like X plus equals symbol minus X shift right learning rate. And this turns out to be exactly what I'm doing in this little compressor. Yeah, that did look like a phi, didn't it? I'm writing it with a mouse. That's just how it is. But anyway, so this is what maybe our model looks like, right? So in this case, the context is everything we've seen before. So we just sort of have one context, which is everything we've seen before. And within that context, we have this prediction, and then we update this prediction after we see every symbol. So then I guess there's the idea of context. And in this case, I kind of got away with not talking about it, even though that's what I wanted to talk about, just by saying that the context is everything we've seen before. So there's one context for the entire file. But maybe we can do better. Let's say our context, instead of being the entire file, we would actually call that order 0 context, because there's sort of no context. It's just like the whole thing. We can do order 1 context. And order 1 context is, instead of considering everything we've seen before, let's have one of these predictions per whatever the previous symbol was. So let's say, let's say we had 2 contexts now. The context if the last bit was 0, and the context if the last bit was 1. And at every position, we use that context instead of a global context. So normally they would both start at 1/2. Whoa. This would be 1/2. Exactly, Procyon. That's exactly what that is. So in this case, here, we don't actually have a previous one. So we're just going to pick one of these. We pick the order 0, or we pick the context for the previous bit being 0. We just kind of assume that this is 0 because we have to make a decision. We could also decide that, oh, we have a third context, which is global, which is what we don't know, but we would only use it for this first bit. So we're just going to accept any loss that we might incur by perhaps getting the wrong statistics here. That's fine. So this predicts 1/2 initially. So 1/2 for the first bit. And then after this, we see it's a 0. So we sort of select this context for bit 0. And then we use it to predict. And then after we see the symbol, we update this same context with whatever that symbol was. So like, let's say L were 1/2. Then this would transition to, because we saw 0, this transitions to 3/4. So then we look at the next bit. Now in this case, we know what the next bit is, so we're going to select the same context again because we're going to predict what this bit is going to be within the context of the last one being 0. So we're going to use this again. So this time we predict 3/4. And then we see it's a 0 again. So this is going to transition again. We're going to update this again to, what is it, 7/8. I think. I might be wrong about these, but it doesn't really matter. So then we look at the next one, and we're still in the context of the last bit being 0. So we're going to still use the same context here. And we're pretty sure it's going to be like 7/8. And then we see that it's a 1. So we didn't do that well, so we're going to probably go the other way. In this case, this over 2 like this is actually going to drop this down to 3.58, which should be 7/16. So we actually went way sort of on the other side of the spectrum. Now we're predicting it's probably going to be 1, because this particular update rule, when L is really high, it really favors more recent statistics. If this were a lot lower, then this would favor longer statistics. Not that important, but anyway, this is transition to 7/16. But then when we predict the next bit, we're actually going to select this other context because the previous bit was a 1. In that case, we're going to predict it as 1/2. And in this case, we've actually done better here. Because last time we predicted what the next bit was going to be as like 9/10, but in this case, 1/2 is actually closer to what it actually is going to be. Or maybe. Actually, I'm wrong here because it is going to be a 0 and we've mostly seen 0. So this actually is a little bit worse in this case. But I guess you can kind of get the idea. So in this case, we transition from 0. So then a 1 in this case. This is still the prediction. It's going to be 1. So this would still transition to 3/4, just like the other one did after we saw the 0 here. And then for the next one, our context is this 0 context again. So we're going to predict 7/16. That this is going to be a 0. And we've actually not predicted that well either, because of how fast our update rule is. So you can kind of imagine, in this case, our order n context just looked at the last bit, and over time this might learn pretty accurate statistics of the file. A real compressor might use like order up to like order 4 or 5 for context, and that tends to do pretty well. For much higher context, you need like a really good learning rate, because you can kind of imagine that as we increase the order of this context, and we're talking, when I say like order 8, by the way, order 4, 5, or 6, that's like order when we're talking about bytes, not bits. So in bitwise terms, that's actually a lot more. But then as you can kind of imagine that shorter sequences of these would occur a lot. So if we were looking at like order 2, then we would say like, okay, what's the probability the next bit's going to be 1 after we've seen 1, 0? And you can imagine that 1, 0 happens a lot, very often. So typically we want like slower learning rates for those. Again, there's a balance here, and it depends on the data, what you actually want. But then when you get to really high orders, like 64 zeros followed by a 1, that context is not going to happen nearly as often. So you want those, if they do repeat, you would like, whenever they repeat, for them to be useful again. So you usually use like faster update rules. But again, you're kind of assuming that every time you see that, then the bit after that is going to match what you've seen before. So yeah, there's a lot of balance things here, but you can kind of imagine that that's more or less how it works. So when we're compressing an n-bit value, or decompressing an n-bit value, I should say when we're modeling an n-bit value, we typically have as many contexts as, so like let's say we have n bits. Let's call this n bits. We usually have 2 to the n minus 1 contexts just for that one thing. So like let's say we're trying to model, if we go back to this, we want to model literals. So let's say a literal would normally be 8 bits, and we want to sort of adaptively model all the literal bits. we would need about 255 contexts just for modeling literals. And we would select which of those contexts we use by mapping the bits of the current literal we've already seen, plus some indicator of where we are in the bits. So like we have up to 8 bits. So we have like the position, and then we have the bits we've already seen. And it turns out you can do the context like C is, let's call this position P, and then the values that we've already seen so far is going to be B. Then you can do this as like 1 shift left P plus B minus 1 will give you one of these 256 contexts to model with. So you can kind of think of it as like we generate context based on some kind of history, and that's just a mapping of some stuff that we've already seen to a number. And then within that context, we have a prediction that we're doing. So the prediction and its corresponding update rule, we generally call that the model. And then this index in this table of those models we have, we generally call the context. That's kind of the main idea. And in fact, I think this is exactly what I use, except since this is 2 to the n minus 1, we can allocate 2 to the n slots, and then we can drop this minus 1, so then we never use context 0, but we always start with context 1, and then that just happens to be smaller in code because you only have to do these things. I think I mentioned earlier that particular unpack loop does a shift left with ECX, and that's actually why it has to be in order to do this shift, I think. Maybe there's a better way I can formulate that, but anyway. This will give you okay modeling of these kind of statistics. So you would have one of these sets of contexts for literals. You would have another one of these sets of contexts for match lengths, and you would have another one for match offsets, for example. And you can get really fancy with this. So like if you kind of put all these in a table, so you'll see at the top of this, I have these number of bits, and then I have the number of different contexts, which is 1 shift left the match number of bits. Again, this should be minus 1, but it's easier if I just keep it like this. And then the total context is all these added together. And so then when I'm going to encode one of the literals, you can see I have the same things here in Rust. Maybe my font size sucks, by the way. I'm sorry about that. Totally forgot. That's actually fine. So here when I'm selecting one of these, where's the actual encoder here? Or the decoder in Rust, which matches the assembler stuff more or less. Here we go. So here we read bits, and then I have a sort of base context and then a number of bits. And so the base context is sort of like I store all of these contexts together in a really big table, and then I offset. So we can do plus base. And then that's actually the entire context selection. In fact, this is this decode read bits thing. So here we have exactly the base context plus 1 shift left I plus the value that we've already decoded. So that's selecting those contexts, and we get a prediction, and then we decode the bit using the prediction, and then we update the prediction in that context with the symbol. This is probably should have shown this, but anyway, this is kind of what we're doing. So when we decode different bits, we supply this different base context. And we could supply any kind of like base context for this, or we could like mix different ones. So maybe we could actually decode literals better if we did something like last byte times 256 plus literal context or something. And then we could get sort of almost like order 2 statistics or order 1 statistics of the literals in addition to like the global statistics we have. Maybe something like that compresses better. And we could mix all kinds of stuff. Like in this case, we always have these packets that always do a length and maybe an offset and then a literal. But maybe if we had a bit that would select if it was a literal or a match, maybe the context to select that bit could be derived from what the last 2 packet types were plus what the last match length was or something. Like depending on the kind of statistics your actual data has, these are the kind of patterns you might be able to take advantage of. So the context could really be sort of any mapping of something you know about the file, but generally we represent it as like an index into a table. in the case of these really heavy context mixing compressors like Pack or Crunchy or Squishy, what those will do is they'll do a hash of the last 8 bytes. And then in that hash, they'll also include the bits of the current byte and the bit position, similar to this kind of thing. And then look that up in a big table. And then that table has different buckets with the different hashes. And so then we try to like find the matching one, and maybe there's an LRU cache for when it might clobber some of that data in order to make that simple. But then that maps to, again, the predictions in the case of like those compressors, we often will model the same context with many models. And what that means in simplest terms is that we might have several different predictions per context. In this case, I think we just had the one prediction per context. So we just get the prediction directly, but maybe there's 3 different predictions with 3 different update rules. And maybe these different predictions work a lot differently. So like one kind of model might be this exact model here. Another one might be, instead of just a prediction and a learning rate, you might have a prediction and a count, so that the more times you use that context, maybe the learning rate slows down. That could be another model. One of the models I really like, and I'll write a lot about this in the blog, but you make kind of an indirect prediction. So you keep track of the last couple bits that you've seen in that context, and then you look that up in a second table. So like every time you see not just a certain context, but then like every time you see that context, you might see, okay, sometimes every time I see that context, I see a 0, 0, 1, 0. Like let's say you had, it's kind of hard to describe this situation, but the point is that like within the same context, you won't always see the same value, but there might be a pattern in the values that you do see in that context. So the first time you see that context, you see 0. And the second time you see that context, you see 1. And then you see 0 twice. The next 3 and 4 times you've seen that context. Maybe the 5th time you see that context, that pattern will repeat and you see a 0, 1, 0, 0 again. So you can map the last few bytes that you've seen that context to a different prediction and then kind of update that with those rules. So that's actually really similar to branch predictors used in CPUs, because again, those are predicting bits too. And in particular, what was that called? I was so happy when I found this connection. A 2-level adaptive predictor in branch prediction parlance is exactly that. And then you might have a model that maps runs. So like you count how many times you've seen a 0 or the last symbol. You keep track of what was the last symbol seen in the context and how many times was that seen. And then as soon as you see the other one, you just count how many times that was seen. And all of these essentially just kind of model some kind of prediction. Like you might even include like bit counts, how many times you've seen 0, how many times you've seen 1. That's what Crinkler does, and earlier versions of Pack did that as well. All of these just represent different kinds of predictions and how they sort of change as the different contexts are used. And so having several of them per context is usually good, because then the context is sort of defining what your compressor is looking at and where it can try to find patterns, and then the models determine what kind of patterns it's allowed to find. So you're essentially, by picking the right context, you're making your compressor look at the right stuff, and by giving it the right models, you're allowing it to understand what's happening in those contexts as best as possible. So you kind of need a mix of both of those, and it tends to be that if you have a lot of predictions and a good way to mix those together, then you'll get better compression. But maybe that's too expensive to do. So oftentimes a lot of these kind of simpler models are used instead. Lots of fun stuff. But yeah, so this particular coder is essentially just trying to parse the data then. The decoder just decodes these really basic. Like this is the entire decoder here, where we have decompress. We load in some initial state for our arithmetic coder, and then we know how many packets there are going to be, and so then we decode the length. We might decode an offset with that, and again, we're doing this with different contexts. And then we're going to copy the match if there was one, and then we copy a literal. And that's as simple as it gets. Does this until it chugs through the whole input. So then again, the encoder needs to be able to produce these packets and figure out kind of the best way through the file. So there's actually really interesting ways to do this, and to do this optimally. Ideally, we would have what we call an optimal parse, and that means that given the way that we're encoding everything and the sequence of bytes that we have literally the smallest possible output bit sequence that we could have. And that gets a little funky when you have adaptive statistics like this, because you kind of have to search through many different ways that you could encode the data. And as you search through those different ways, you kind of have to propagate what the different model state would have been along those different paths. So there's really interesting ways you might actually do this. One of the ways that I found was on Charles Bloom's blog. Let me pull this up actually, because this was a cool find that I found the other day. And I guess this was called, what do you call them? Chain N parse or something. I don't think this was a new idea. I mean, this blog post is from 2015. But what did he call it? He called it like a forward chain N parse or something. And I ended up implementing this because it was pretty good. And it was interesting. But the idea is that what you can do is, like, for every position in the input. So we can go back to, I'll just start a new one. I'm having fun. Are you guys having fun? Or am I just rambling and talking to myself for an hour? Whoa. So the idea is for each position that you have in the input here, nice, Chris. Fair enough. So for each position, what you can do is you can store a bunch of different ways that you could have gotten to that position. So you do sort of a forward pass on the data where you say, okay, the only way we could have gotten to position 0 is, well, we started at position 0, so that doesn't really count. But from position 1, okay, we could have gotten there from encoding a literal here. So we call these different arrivals. So like, let's say this, we could say lit A, and then some information about where that came from. And then at this next position here, we could have gotten here by encoding a literal A from here. So a literal, let's see, literal A from here. We also could have gotten here by doing a match from here, and so on. So then at this position, we could have gotten here by doing another literal B. And I think the only way we could have gotten that was from here. So the way you do this is you look at every position and you look at the different things you can encode from there. And you store all the things you could encode at the target positions. So if we encode a literal A from here, then we could get to this position that came from here. We could also encode a match from here, and then we'll get to this position again. And it came from doing a literal, or doing a match from here. At the end of this, you have several ways you might have, several sort of arrivals that you could have gotten to from all these different positions. And like, I'm just fudging this here, but let's say there was an arrival here that came from this, and another one that came from this. And so what you can do is you can look at the cheapest arrival here, and that will tell you the exact path that you would have taken to get there from the beginning of the file. So if you walk that backwards, you have literally the sequence of things that you want to encode in the reverse order. And you could, for example, store all of the different ways you could arrive at each position. That tends to explode in memory. So typically what you do is you would do like 4 of the best arrivals that you could have found. And then you just have like a little L or U cache at each one of these places that contains the 4 best arrivals. So at the very end, you just take the best one and walk that backwards. But then for each position, you might have a couple. And for each one of these, you actually want to test all the different ways you can encode the data from both of these positions. Because maybe this one, it was a little more expensive to be here than to get to this position from this arrival. But if this one can lead you down a path where you encode symbols that work better with your model and everything, that gets you to a farther position cheaper than this one would have eventually, you want to be able to explore that. So that's why you want to have like sort of different potential arrivals at positions kind of running in parallel. This ended up being actually pretty nice to implement in Rust. I model. I did this pretty brute force. So my model contains all the different contexts. And I have another version of this too that has like repeated offsets in some of the matches too. And then that also has to like propagate some of that state, but it's the same basic algorithm. So the parse here, we allocate this arrivals array. So we have no arrivals times 4 for all the different positions. And then we essentially generate these little packets. So in this case, there's a packet with just the literal, and that represents one way that we could jump to the next symbol. And then we can generate all the different matches where we actually search in the previous bytes and find matches. And the ones that we can encode at our given position, we're going to test all of those. And so for each test at a given position, we test as if the packet came from all the different arrivals that are at our position. And then for that test, we create an arrival, which contains the packet we used to get there, the total cost of the bits for that path, where it came from, and then the current model state after we follow that. And that gives us everything we need to just continue for the entire parse. That's essentially the whole algorithm. So then we create that new arrival, and then we just test to see if it's worth putting in as one of the best arrivals for the target slot. So then at the end of that, we have the best arrival at the last position. So we're going to walk that backwards here, and then collect all of the packets that path was made out of. And then we're going to go ahead and reverse that, and then actually encode those. And that's the whole thing. And with this small data, we can afford to do like a brute force search here when we're actually searching for matches. And we can afford to have 4 of these in parallel. And we can afford to copy the entire model state for all of those different arrivals too. And it's cheap enough and fast enough. Whereas the decoder doesn't really care, because the decoder is only going to follow like the one path that the encoder chose. So the decoder just needs one copy of the model that it's going to update, and that ends up being a lot simpler. Anyway, I had a lot of fun with that. And then a lot of that, once you have a parse that can take into account like the different model statistics and everything, then you want to go back and like tweak what your learning rate is, tweak the initial model states, tweak the different numbers of bits and everything, because maybe a certain number of bits works well when you're doing entropy coding, and you don't have a great parse. But then when you have an optimal parse, maybe like propagating that model state, it makes sense to start adjusting bit widths. Maybe 11 bits was better when it was uncompressed, but maybe now that we have this parse state, because of how our model works and the way the data is laid out and the way our parse works, we're going to find better paths if this were more or less bits. And I think I ended up with, like, for example, more offset bits than I had before, but less length bits than I had before, because that ended up working better with this particular setup. And I actually did a version of this where I did a brute force search for all of these parameters. And these ended up being the best ones. Now this encoding is still rather limited. Like, the packets always have a match, and the packets always end with a literal. There might be more things to do there. I also tested repeated match offsets, so it's really common that if you have a match, the next match, or if you have a match somewhere, it might be able to reuse an offset that you've already encoded. And then you don't want to encode that match again. You just want to encode the fact that it used the last match offset. So then your model also needs to include the last match offset, or maybe the last 5 or something. And then you want to encode different ways to predict if you're going to use a repeated match or not. So there's a lot of different ways you can sort of build context. And then maybe there's patterns in some of those contexts depending on the data that you're compressing. It really depends on a lot of things. So you gotta just try a lot of stuff with this kind of thing. At this point, though, there's a couple more things I want to try with this particular compressor, but I'll probably just use the Windows compression API to do this job, just because the decompressor is not free, but a lot smaller than a handwritten one. But we'll see. Anyway, I'm kind of running out of things to just talk about. If you guys have any questions about any of this, I'll go ahead and try to answer those. But if not, and or when you guys are done with that, I'm gonna go. Oh yeah, see ya, unconditional branch. Sorry if you already left and missed me saying that. Yeah, here's also the time where I put the disclaimer that I'm not by any means a compression expert. This is all stuff I've learned in like the last 2 years. And I'm always learning this stuff, like that parse technique where you do the forward arrivals kind of parse. I just learned that the other day. Sounds good, Paros, yeah. Yeah, this is like one of the simplest possible incarnations of this kind of parse, just because we have so little data. You'd want to do this a bit smarter if you had more to do. Procyon, I probably will never actually release the source to the Packer. Maybe in a long time, but the demo scene has a big problem with compressed intros being flagged by antivirus scanners. And one of the ways to mitigate that is to not make your Packer public. So that's still up in the air. I may never actually release it, but the blog post that I'm writing will at least describe all this in great detail with a lot of links to other places where you can find the different pieces. So if you want to build like a Linux Packer, that's probably a pretty good place to start. Crunchy's also open source, so maybe you could hack that if you wanted, Elf. I mean, yeah, Squishy gets a bit better compression because it uses a lot more cycles in memory, but a lot of the core ideas are the same except the way it does executable modeling, which is just a bit more general, but still the same kind of ideas, just computers are faster. But yeah, I guess that's it. Thanks, guys, for hanging out. I appreciate being able to just rant like this and have an audience, and I hope you guys enjoyed this. Yeah. Anyway, thanks, guys, for hanging out. I'll see you next time.